Welcome back. So far we are already done with the understanding of SPC and the most widely used type of control chart, that is X bar R chart. But it is always good to know all the options. So here in this lesson we will go through other types of control charts. Let's begin. The selection of which control chart is to be used depends on the data type. If our data is continuous, we use variable types of control charts, like the X bar R chart. We have seen this in the last lesson. In the X bar R chart, we generally take a subgroup size of 5. But if we can afford to increase our subgroup size to more than 8 or 10, it is better to use X bar S chart. The only difference is, in place of range R of the sample, we will plot S, standard deviation of the sample. Centerline will be S bar, and control limits are calculated using the other control limit factors from the table of constant. The S chart gives better understanding of the spread or precision than the R chart that only provides the difference between max and min value. On the other hand, if we cannot afford to inspect more than one part in a subgroup, we can use the XMR chart, that is individual and moving range chart. Here we inspect only one part in a subgroup and there are no averages, so we directly plot the individual value X, and the moving range MR is calculated as the difference between individual value of this subgroup minus the individual value of the previous subgroup. That is why we call this moving range. You can see now that X bar S chart are most accurate, but it demands bigger sample size. XMR chart needs only one sample per subgroup, but it is not so accurate. X bar R chart is like a midway between these two, and it gives fairly accurate results with reasonable sample size. That's the reason it is the most popular type of control chart. Now if our data is discrete, we use attribute type of control charts, and further depending on what we want to study, we can go for counting either the non-conforming parts, that is undersized parts, leak parts, not working parts, etc., or the non-conformities per part, meaning there could be multiple defects in one part. For example, number of visual defects on a painted surface or a mirror, like 3 scratches, 5 bubbles, 1 hairline crack, something like that. While counting non-conforming parts, we can either go for a P chart if our subgroup size can change over time. Here we plot values P, that is proportion of NP, number of non-conforming item founds, and N, number of parts inspected. Centerline will be P bar, which can be calculated as the total number of non-conforming parts found divided by the sum of sample size. Just make sure that the sample size is such that if we multiply P bar with the sample size N, it should be more than 5. And if our subgroup size is constant, we can go for a NP chart. Here the individual values will be NP, number of non-conforming parts in a subgroup, and the center line is the NP bar, which can be calculated as the total number of non-conforming parts found divided by the total number of subgroups. Simple. Similarly, for counting non-conformities per part, when our subgroup size can vary, we use U chart, where we plot U, that is proportion of C, number of non-conformities found, and M, number of parts inspected. Centerline will be U bar, which can be calculated as the total number of non-conformities found divided by the sum of sample sizes. And if our subgroup size is constant, we can go for a C chart. Here the individual values will be C, number of non-conformities in a subgroup, and the center line will be C bar, which can be calculated as the total number of non-conforming parts found divided by the total number of subgroups. That's it. Should you need to study deeply about the control charts, I recommend going through the AIAG SPC manual and a few more books of your liking. But as I mentioned earlier, our objective here is not to become an SPC expert, but to have a deeper understanding of our process. Before ending this lesson, let me discuss one more concept. Once the process becomes in control and the customer specifications are met, we generally keep on monitoring the trend using the control chart. But there is no effort to further improve the process. I mean, why put your resources if the target is already met? This thinking comes from the goalpost mentality. That means believing that all parts within specification, regardless of where they are located in the specification range, are equally good, and parts outside the specifications are equally bad. There is a problem with this approach. To understand this, let us understand why there is a provision of tolerance in the design. Ideally, the product designer wants the product to be exactly at the target value, because as the distance from the target value increases, there are more chances that it will not meet the functional requirement. But variation exists. So the product designer decides a range that is big enough to take care of the constraint of the production process, that is the natural variation, and at the same time this range has to be small enough so that the customer remains insensitive to this variation within the specifications. This carefully calculated range is reflected in the engineering drawings as tolerances. But that doesn't mean all parts within the tolerances are equally good. The quality professionals suggest loss function mentality, where we plot a loss function curve in this goalpost. The farther a product lies from the intended target, the more will be the loss in function in terms of time, cost, or efficiency. If I superimpose the original process curve, the inverted bell, we can see that we are producing parts that may be okay according to the customer specification, but there is a loss of function, and if I improve my process in location or spread, this loss can be minimized. So, it is the continuous cycle of analyze, maintain, and improve, even after meeting the customer specifications. Alright? That's all for this series. I hope I have made a few concepts clear to you. In case you have any questions, you can ask in the comments below. Thank you for your time. Have a nice day.